we will start linear programming. In this new chapter, we will be going through linear programming problem. In short, we refer it as LPP. Then we will discuss the method to solve LPP, that is simplex method. So we will understand its basic, and then we will solve a problem so that we can see how this simplex method works. Thereafter, we will discuss the dual phase method, in which the LPP has a different structure. So how to solve such kind of LPP. Sensitivity analysis is discussed at the last. This sensitivity analysis is important because at the end we will discuss Lagrangian multiplier that are being used with the nonlinear optimization. We will conclude this chapter at the last. Let us begin with the linear programming problem. Now, LP methods solve optimization problems having linear objective, function, and constraint. So when we talk about linear programming, so the formulation, basically the objective function and constraints, all of them are linear equations. Such kind of equations or the formulation of an optimization problem, that is LP, that are extensively used in operations research and the transportation problem, where the objective function and constraints are linear. LP methods can also be used for solving NLP. So NLP stands for nonlinear programming problems. So in the previous chapter, when we have discussed about the multivariable optimization, so the problem which we have solved, that is Hamel-Blau function, it is one of the NLP problem. Similarly, there are many problems which are nonlinear in nature, and that's why those problems are called as NLP. Now, when we are solving such kind of NLP, after approximation, we can use the LP methods such as simplex method to solve them. So linear programming problem, what we know that the constraints are linear. It means that the feasible search space that is closed and closed by the constraint is linear hyperplane. So that feasible search space will become the linear hyperplane. Now, since for this linear hyperplane feasible search space, when our objective function is linear, the optimum solution is usually one of the corner point, as you can see at the bottom of the feasible search space, that we will see, except for some special cases, the optimum solution will be one of the corner points of the feasible search space. Now, if we write an optimization formulation for LPP, we want to say maximize our function fx, which is c1 x1 plus c2 x2 till cn and xn. So as you can see, this is the linear equation in X, where C1, C2 are the coefficients, or we can say cost coefficients. Similarly, if we look at various constraints, so you can say we have B1, B2 till J. So we have J number of constraints, and all equations, as you can see, are linear equations. And the left hand side is equals to the right hand side. At the last, we also look for the non-negativity condition, where each variable should be greater than and equals to 0. In this particular scenario, we have n number of variables and capital J number of constraints. If we want to write in a short form, we can write in the form of matrix and vectors. So the objective function maximize C transpose X is the same equation on the top, where C is the column vector corresponding to the cost coefficients, and X is a column vector of variables x1 to xn. So I have written as x1 to xn transpose. So it's a column vector. Now this problem is subjected to Ax is equals to B, where A is the coefficient matrix, and inside this matrix, as it is written, A11 to A1n, these are all the coefficients corresponding to equation number 1 in constraint. Similarly, if we look at AJ1 to AJN, These are the coefficient corresponding to the last equation in constraint. The size of this particular matrix is J cross N. We have J number of equations and N number of variables. Similarly, AX is equals to B. The B is the right hand side coefficient, which we write as B1 to Bj, and it's a column vector. And we can write the vector X should be greater than 0. So this representation, we will use it later. Now, in the previous formulation, we have gone through the equality constraint, but as we know, we can have inequality constraints as well. In this situation, we use slack variable to transform the equality constraint into transform the inequality constraint to equality constraint. Let us see how. So suppose we have Gj of X smaller than 0. So this is one of the inequality constraint. So what we will do on the right hand side of this smaller than sign, we include one variable called xn plus 1, and this variable is referred as a slack variable, and the value of this variable should always be greater than 0. Similarly, we can have inequality constraint in the form of Gj of X greater than 0. In this case, we subtract our inequality constraint. We subtract the slack variable, as you can see that Gj of X minus xn plus 1 equal to 0. So what we are doing, we are converting these inequality sign into equality sign by either adding or subtracting the slack variable. Usually what we found that the number of variables is large than the number of constraints. So in this case, the equality constraints can be used to express J variables in terms of other N minus J variables. So this particular concept, we will use it in the LPP. So let us rewrite the row echelon form. So since we can write x1 to xj in the form of other variable, so x1, x2, xj, you can see they are written in this form. And the other part, that is the other variable from j plus 1 to n, they are written with the help of other coefficients. Since we have converted the equation into the row echelon form, our right hand side vector, which is v1 prime, v2 prime and bj prime, will change. So you can see that the original problem formulation which we have discussed, that has to be changed so that we can get row echelon form here, and correspondingly the coefficients will change as well as the right hand side of the equation b1 prime, b2 prime, bj prime will change. Now let us rewrite this row echelon form into the vector and matrix form. As you can see from the coefficient of x2, x1, x2 and xj, that makes an identity matrix. So as you can see, we are starting with an identity matrix here, and this matrix is multiplied by with a vector from x1 to xj. Then we add. So now we have a coefficient matrix. So we have this coefficient matrix from which contains a1 j plus 1 to a1n, and similarly at the last row aj j plus 1 to ajn. This cost coefficient matrix is multiplied with the corresponding variables starting from x j plus 1 to xn, and equals to the right hand side is written in the vector form, so the column vector. Now here I'm introducing two types of variables that are called basic variables and non-basic variable. So let us look at this row echelon form. As we know that x1 to xj will be expressed in the form of other variable. So these variables will become dependent variable. So these dependent variables are referred as basic variables in our LPP and simplex method. And the other variables that are from xj plus 1 to xn, these variables are independent variables because they can take any value. Therefore, at the bottom, you can see The variable from xj plus 1 to xn can take any value because they are independent variables. So these are called non-basic variables. So we will be talking most of the time in basic and non-basic variables. Now the row echelon formulation, the coefficient corresponding to basic variables are always 1. So we perform some operations so that we make sure that the coefficient of x1 is 1 and there is no coefficient from x2 to xj because all of them are 0. Similarly with x2, similarly with xj. So that's why these column corresponding to the basic variables, they always be a part of identity matrix. And also the right hand side should be non-negative. Bj prime should be non-negative. Now for the given system of this linear equations, what we know is that the number of variable is more than number of constraints. If this is happening, so there will be infinite many solutions. So in this particular case, what we do, we assign all non-basic variables 0. Why? Because they are independent variables. So they can take any values. And where by assigning the 0 value to non-basic variables, we compute values of basic variables. So the basic feasible solution is defined as solution at which all basic variables are non-negative and all non-basic variables are 0. So you please make out a difference between basic and non-basic. That basic variable should be non-negative and non-basic variable should be 0. If we try to find out how many such kind of basic feasible solutions are possible for this system of linear equation, so we have n choose c number of basic solutions, basic feasible solution. Now, if we want to solve such kind of LPP, we have method called simplex method. So the main concept of the simplex method is to compare neighboring basic feasible solution in an efficient way. So rather than we will be searching, we will be just looking the neighboring solutions, and by moving from one neighbor to another neighbor, we try to find out where is the optimal solution for LPP. So what will happen in this simplex method? We start whatever be the set of basic variable we have. So one basic variable in the current basic feasible solution is made non-basic, and one current non-basic variable is made basic, meaning that suppose there is a variable x1 which is basic. So if we are converting into non-basic, so x1 will become 0 automatically. However, if suppose there is a variable called xj plus 1 which is non-basic right now, and we can make it basic, and we generally perform so that our objective function should improve. So I can do it I can find different ways to know that converting basic into non-basic and non-basic into basic. So we have j times of n minus j different ways. Now question is, if we are converting basic to non-basic, non-basic to basic, so which of the non-basic variable is to be chosen for the basic variable? Similarly, which of the basic variable is to be chosen for the non-basic variable? So answer to this question, we have two conditions in the simplex method. First is called optimality condition. As I mentioned here, optimality condition for maximization type of objective. So the simplex search method chooses that non-basic variable which causes a maximum increase in the objective function. So since we have so many non-basic variables, so we will be choosing the one which will increase our objective function maximally. So this is the optimality condition for choosing the non-basic variable. And then we have a feasibility condition. So point is that how do we know that this optimality condition it works? So basically, if we are going to change this non-basic variable from 0 to 1. So as you know, non-basic variable should always be 0. But if we are making from 0 to 1, is it going to affect our objective function? If yes, then we will be looking for the uh, maximal improving the variable corresponding to the maximal improving the objective function. This we can find out by computing this factor or the value which is called delta FQ. Now Q stands for the current non-basic solution. So we find this particular factor. So when I will be solving a problem, then it will be clear what is that. So CQ, so this is the cost coefficient corresponding to the non-basic minus we are subtracting some set of cost multiplied by the coefficients. And this computation we perform for all non-basic variables. And when this delta FQ value, which has the maximum positive value, we choose that variable Q for maximization problem. Again, I am mentioning maximization because for minimization, this condition will change. Now suppose if any of the iteration, if the delta FQ value for all non-basic variable is non-positive, it means that it can be 0 or smaller than 0. So this says that there is no non-basic variable that can be made basic, or it can improve our objective function further. So in that case, we should terminate our algorithm. So first condition was optimality. Now another condition is the feasibility condition. So once a non-basic variable xq is chosen, the next question is which of the basic variable has to be made non-basic. So now our task is converting basic into non-basic. So in this case, now since we have already chosen that solution Q is going to be our non-basic to become basic. So this value we are going to increase it. So when we increase this value from 0, because xq is currently a non-basic solution. So if we change this value from 0 to some positive value, then we have to look which basic variable will become 0 quickly. So in that case, when we find such kind of a variable which will become 0 first, that variable will become our basic variable that should be converted into non-basic. So in this case, let us assume that we have this basic variable xj and the value is written in this form. Thereafter, since we have to find which basic variable has to become 0, so we are making this equation equals to 0. So in a way, what we are doing is we are saying that xq is equals to bj prime divided by a prime jq. Now, if we look at this xq equation here, we know that bj prime is non-negative. We also know that xq should also be non-negative. Then a prime jq should also be negative or a positive. So non-negative includes 0, so it should be positive. Otherwise, it will take an infinite value. So in this case, what we will do, let us compute this particular ratio corresponding to the basic variables, and let us identify basic solution, say P, which has the minimum ratio. Why? Because this minimum ratio says that this is the basic solution that will become 0 first among the set of basic variable. While we will be solving a problem, there are one column called pivot column. So as of now, we know that the optimality condition will help us to find out which particular non-basic is to be made basic. So if we look the column of that entering non-basic variable, so that column is referred as pivot column. Similarly, the feasibility condition says that which basic solution will become non-basic. So we will be looking for that row of basic variable, and that row will be referred as a pivot row. Now the common intersection of pivot row and pivot column gives us pivot element. It has a role. Why? Because when we are converting the non-basic to basic and basic to non-basic, we have to change our simplex table. So we are going to make a table with simplex method. So the coefficient under the table should change accordingly. So the Gauss-Jordan row operation says that first operation we have to perform for pivot row. So that pivot row is the new row, which is equals to the current row divided by pivot element. Now you can see the pivot row and pivot element have come into the picture. Thereafter, we look for the other rows. So other row says that what is the current row minus we have to look the pivot column coefficient corresponding to the same row, and we multiply new pivot row. New pivot row we just calculated in the previous step. Now there are three steps which are involved in simplex method. First is we have to choose a basic feasible solution and set all non-basic variables to 0. This is a very important step. Why? Because simplex method always starts with a basic feasible solution. Once we know, then in step 2 we calculate delta FQ. Why? Because we have to check the optimality condition first. By checking the optimality condition, we will find which non-basic variable can be made basic. If suppose this delta FQ value is smaller than 0 for all non-basic variable, then we should terminate the algorithm, because there is no variable which can further improve the objective function. However, if it is not the case, then we find the feasibility condition in which we will find the minimum non-negative ratio. So we'll see how when we will solve the problem. So step 2 will identify entering non-basic variable, leaving basic variable. Then there will be corresponding changes in the simplex table. So step 3, we will be performing a row. We have to perform a row echelon formulation using Gauss-Jordan row operations for new basic variables and other rows as well. And then we go to the step 2. So we will be keep on moving between 2 and 3 till this termination condition gets satisfied. So let us understand the simplex method with the help of one problem, as it is stated here, that we want to maximize a function which is equals to 2x1 plus 3x2. This problem is subjected to x1 is smaller than 6, x1 plus 2x2 is smaller than or equals to 10, and x1 and x2 should be greater than 0. The plot is drawn in the right hand side. Now here you can see the vertical line x1 is smaller than 6 is the first constraint, and the left part of this particular constraint is feasible. How we will find it? If suppose let us take the origin. So at this origin the value of x1 and x2 both are 0. So if I put x1 equals to 0 in this constraint, so this says that 0 is smaller than 6. Yes. So this means that the direction of the direction for the feasible area is from this line towards the origin. Similarly, we have another constraint called x1 plus 2x2 smaller than 10. This is shown in the another color here. Now we have to find which area will be feasible for us. So again, let us look at the origin 0, 0. If I put the value, so 0 plus 2, 0 means 0. Is it smaller than 10? Yes. So what I will do is I will look from this particular line towards the origin. So that is the area which is feasible according to this constraint. Now look at the non-negativity condition, which is x1 and x2 greater than 0, which says that the first quadrant is feasible. So as you can see, I have written x1 and x2 greater than 0, and this hashed line we are drawing just to show that these are the constraint lines. Now, if we are trying to find out what is the common area that will become the feasible search space. So as the shaded region suggests, this is the feasible area for the given problem. So let us solve this with using simplex method. So step 1 says that we have to convert all inequality constraints into equality constraint using slack variable. Now, if I go back, both of the constraints x1 is smaller than 6 and x1 plus 2x2 is smaller than or equals to 10. Both of them are smaller than and equal to type constraint. So this means that we have to add a slack variable on the left hand side. So the modified equation will become x1 plus x3. Now we have added a slack variable x3 and converted the inequality constraint into equality, which is equals to 6. Similarly, the second constraint is x1 plus 2x2 plus, now we have added a slack variable on the left hand side equals to 10. So both of the constraints are converted into inequality. And the non-negativity condition stays the same for all the variables such as x1, x2, x3, and x4. All of them should be greater than and equals to 0. In this current scenario, we have 4 variables from x1 to x4. We have 2 equations, that is the first and the second equation, as you can see. This means that the number of basic variable will be equal to the number of equation, that is 2. And the number of non-basic variable will become n minus j, that is 2. So number of basic and non-basic in the current example is 2. Now, step 2 says that we have to basically find what are the basic and non-basic solutions, and then we will apply our optimality condition followed by a feasibility condition. Now question comes that we have 4 variables now, x1, x2, x3, and x4. Then which of the variable I should take basic? So now we have to take 2. Why? Because j is equals to 2. So the thumb rule says that let us look at the equation number 1, x1 plus x3 equals to 6. In this particular set, we will choose the slack variable as a basic variable at the beginning. So at the beginning, we will consider x3 as a basic variable for equation 1. Now coming to equation number 2. Now in equation 2 as well, we have x4, which is also slack variable. So that also should be taken as a basic variable in the starting. So x1, so that's why we have taken x3 and x4 as a basic solution. Now we are drawing the table. Now you can see this table. So in this particular table, let us start from the second row. In the second row, first we draw the column corresponding to CB. So this is a cost coefficient. Then we have a basic, means what are the basic solutions. Then we will be writing coefficients of x1, x2, x3, and x4 in both the constraint equation. And then RHS means right hand side. So the right hand side of the equality, we are going to write it. So now coming to the row number 1. So this 2 and a 3, these are the coefficients of the x1 and x2 in the objective function. So you remember that we want to maximize a function 2x1 plus 3x2. So that's why the coefficient of x1 2 is written, then x2 3 is written. However, for x3 and x4, 0 are written on the first row. It is because they have no contribution in the objective function. Now in a step 2, as we have decided, x3 and x4 are going to be the basic variable. So for equation 1, x3 is the basic. For equation 2, x4 is the basic. Now look at the CB column. We have written 0 and a 0 because the coefficient of x3 and x4 in objective function is 0 and 0. So that's why we have taken 0 and a 0 here. Now look at the x3 row. In this x3 row, we have written the coefficient 1, 0, 1, 0, 6. So these are the coefficients. So let us look at the equation on the top. So let us find out the coefficient of x1, x2, x3, x4 and the right hand side. Then you will realize it is 1, 0 for x2, then 1 for x3, 0 for x4, and then 6. So same coefficients are written under x3 row, 1, 0, 1, 0, 6 in the table. Similarly, look at the x4 row in the table. Now I'm coming to the equation, the second equation from the top. So the coefficient of x1 is 1, coefficient of x2 is 2, 0 coefficient for x3 and 1 coefficient for x4, and right hand side is 10. Now coming to the table, look at the x4 row. We have 1, 2, 0, 1 and 10. Same coefficients we have written. Now since we have made this initial simplex table here, now let us see what is this solution. Now you know that in the current iteration, x3 and x4 are non-basic solution and x1 and x2 are basic. Let me repeat again. From this particular table, we know that x3 and x4 are basic solution and x1 and x2 are non-basic solutions. And non-basic solutions are always 0, that we know. So if we look at this particular graph here, we are representing this in terms of x1 and x2. Since x1 and x2 are 0 in the initial simplex table, meaning that we are starting from the origin. This origin, we are saying that it is a starting basic feasible solution. So simplex method can start. Why? Because it has to be start from the feasible solution. Now apply the optimality and the feasibility conditions. Now we know that we first apply the optimality condition in which we find this delta FQ. Now currently Q is corresponding to solution 1, which is x1, and solution 2, which is x2. So how I get this delta FQ1? Now I'm looking at the column corresponding to CB, and I'm looking the column corresponding to x1. So if I have to find delta F1, so let me see the coefficient of x1. This is C1, which is 2 minus. Now coming to the CB column. So 0 multiplied by 1 plus 0 multiplied by 1. So it is 0. So these things, as you can see on the left hand side, C1 minus C3. C3 is the cost coefficient of x3. A11 is the 1 and minus C4. C4 is the cost coefficient of x4 in objective function and A21. So since these two multiplication are 0, so this is 2. Similarly, I can find delta F for the variable 2. So I'll get delta FQ for both the non-basic variable x1 and x2 as 2 and a 3. The optimality condition says that we have to take maximum positive value for maximization problem. So in this case, solution x2 or the column corresponding to the x2 should be made basic in the next iteration. So the non-basic variable x2 will become basic in the next iteration. So we have identified which is going to enter. Now we have to find out which basic variable should leave the table. Now in this case, how we find? So you remember that we have to find the ratio and then find which is the minimum non-negative ratio. Now looking at the table at the bottom, since x2 is entering into the table, so the coefficient of x2 are 0 and 2, which are shaded in the purple color. Now when we have to find the ratio, so right hand side, which is 6 divided by the coefficient under the same row, which is 0. So 6 divided by 0 is infinite. And for the second, 10 divided by 2 is 5. Now from this, you can make it out that the minimum non-negative ratio is 5. So meaning that x4 should leave. So in this particular case, x2 is going to enter and x4 is going to leave this table. So in this case, as we have identified, now we can see what are the pivot column and pivot element. You know that the column corresponding to the entering variable x2 will become pivot column, which is x2 now, and the row corresponding to the leaving variable, which is x4, will become the pivot row. So the intersection of pivot row and pivot column is the 2, which is shown in another color. Now, once we have identified which is going to leave, which will be entering into the table, we have to perform the Gauss-Jordan row operation by following the formula given earlier. So new pivot row is the current row divided by pivot element. So current row, which is corresponding to this x4. So new x2 row will become all the coefficients I have written, including the right hand side 10 divided by 2. So I get the coefficients. Similarly, for the other row, the current row minus its pivot column coefficient. So what is that? Now let us look at x3. Now, as we know, x2 is going to enter. So in x3, the coefficient corresponding to the entering variable is 0. So that's why in the equation of x3 row, we have taken the row, current row minus 0 times of the new pivot row. So that column will remain the same. So the new simplex table which you can get here is like this. So row 1, row 2 will remain the same. Now look at the CB and basic. Now the column of the basic, we have x3 and x4 is replaced by x2 because x2 is now entered. Now since x2 has entered, now look at the CB column. The coefficient is changed to 3. It is because the cost coefficient of x2 is 3 in the objective function. Now the coefficient under x1, x2, x3, x4 for both x3 row and x2 row, we have already calculated earlier and we have written the value as it is, including the right hand side. Now let us see how this solution has moved. So we started from the origin and then optimality condition says that let us move in the direction of x2. So that's why in the x2. Thereafter, feasibility condition says that minimum non-negative ratio that suggests that we should come at the point called this green point, which is the solution after iteration number 1. Now, since we have performed the row Gauss-Jordan operations, now we are at this step 2 again, and this is the new simplex table. Now we know that in this step 2, first we have to find the delta FQ value. So delta FQ values are written here. So here in this particular step, the two non-basic solutions are x1 and x4. How I would know that? Since x2 and x3 are basic, the rest of the solutions are non-basic. So which are x1 and x4. When we calculate delta FQ value, you can see the maximum positive is corresponding to x1. Now, since we have identified the x1 is going to enter, then the coefficient under x1, which are 1 and 0.5, are taken to find the ratio. So when right hand side is divided by these coefficient, so you can see 6 divided by 1 will become 6, 5 divided by 0.5 will become 10. So the minimum ratio is 6. So x3 is going to leave. So delta FQ says that x1 will enter and feasibility condition says that x3 should leave. Here you might have seen that I am writing a function value as well. How I am getting this value? So what we do here is we look at the two columns, CB column and the right hand side column, RHS. So we multiply the cost coefficient 0 into 6 plus 3 into 5. That makes our objective function 15. At this iteration, what is our solution? X2 is 5. So what we do, we look at the basic column and the right hand side. So the x3 is equals to 6, x2 is equals to 5, and the other variables are non-basic, so they are already 0. Now, since we have identified that x1 is going to enter, so this is corresponding to the pivot column, and x3 is going to leave, then the x3 row will become the pivot row. The intersection means the pivot element is 1, which we can find here. By identifying all these, we can apply our Gauss-Jordan row operation. So the coefficients are given here. So I suggest you to go through the perform some hand calculation in your notebook so that you can understand how we are going to get new pivot row, which is x1 row, and other row is as x2 row. So the new simplex method, you can see now x1 has entered. So now I'm looking at the column corresponding to the basic. So x1 has entered, x2 is there. Now since x1 has entered, now look at the CB column. So the number 2 is written. Why? Because this is the cost coefficient in the objective function of x1. So by doing so, we are writing now the coefficient which we have calculated using Gauss-Jordan operation. So corresponding to x1 row, we have written all the coefficient, including the right hand side. Similarly for x2, we have written all the coefficient, including the right hand side. Now, at this particular stage, if we find the delta FQ value for non-basic variables, which are x3 and x4 currently. So these both of the values are negative, meaning that there is no way we can further improve our objective function. So we should terminate. So in this case, since the delta FQ values is smaller than 0 for all non-basic value, we should stop our simplex method. Now, as I defined you earlier, what is the solution? Look at the basic column and the right hand side. In this case, x1 is equals to 6 and x2 is equals to 2 is the optimum solution. And what is the objective function value? Look at the CB column. So coefficient 2 is multiplied by 6 plus coefficient 3 is multiplied by 2. That makes 18. So in a one simplex method, you will get the solution of x1 and x2, as well as you can calculate the objective function value. If we look at graphically, we started with the basic feasible solution, which is the origin. Then we move to the green point after iteration number 1. And in another iteration, we move to an optimum solution, which you can see in the graph. Now up to here, we have solved a simple problem where the simplex method works very well. But there is another method called dual phase method. So in this dual phase method, you will realize that there are certain changes in the set of constraints. And at that case, we need some variables called artificial variables in our formulation. And as soon as the artificial variables come into the picture, we have to use dual phase method. So as we know, LP starts always with the initial feasible solution. If not, then we have to include the artificial variable to obtain the basic solution. This can happen when you have different kind of constraints equation. We will see later. So in this case, what we will do is once the basic feasible solution is found, the artificial variable can be discarded because they are no use. So word artificial suggests that we are using these variables to get a basic feasible solution so that the simplex method, which we have used earlier, can be used as it is. Now, in this dual phase method, we actually solve the problem in two phases, as the name suggests, dual phase. Phase 1 says that we have to first find the basic feasible solution. Once we get it, then in phase 2, we find the optimum solution starting from the basic feasible solution obtained in phase 1. So we are starting from the phase 1. So let us solve one problem here. This is the same problem. We are maximizing the objective function, same function, subjected to x1 is smaller than or equals to 6, x1 plus 2x2 is smaller than or equals to 10. Now there is a third constraint, which is something new. x1 plus x2 greater than or equals to 2. Now look at the inequality sign. For first two constraint, it is smaller than or equals to 0. So there we added a slack variable. But as and when it is greater than or equals to 2, this means that we are going to subtract the slack variable. So in such kind of a situation, we have to use artificial variable. It is important to know that if any constraint, equality constraint is given in the function, then that equality constraint should also have the artificial variable. Now, and finally, we have x1, x2 greater than 0. Look at the graph on the right hand side. We can see x1 is smaller than 6, x1 plus 2x2 is smaller than 10, both the constraints. Now, as soon as this third constraint has come, you can make it out x1 plus x2 greater than 2. So the feasible search space has been changed. And in this case, earlier we have started from the origin. Now origin is infeasible. And that's why this dual phase method will help us to find out the basic feasible solution for simplex method. So let's see how it works. So we will start with the phase 1 now. So in first step, we have to convert all inequality constraint into equality constraints using slack variable. Now in this particular case, phase 1 says that. So I will talk about this objective function later. Let me discuss the constraint first. Now the first constraint, as you remember that x1 is smaller than or equal to 6. So we add a slack variable x3. So x1 plus x3 is equals to 6, right? Similarly, the second equation, x1 plus 2x2 plus x4, which is a slack variable, equals to 10. Now coming to the third, which was in a different form. So x1 plus x2 minus x5. So this x5 is going to be a slack variable which we have subtracted. In this scenario, we add one artificial variable that is called x6 and equal to 2. The number of variable we have 6 now, and all of them should be greater than 0. So the what phase 1 says that if whatever be the artificial variables we have to make them 0 or non-basic. In this particular 3 set of equation, we have just one. But if we have more, then we have to take all of them. How? So we want to minimize function r is equal to x6 because x6 is the artificial variable. If we are going to minimize it, so what is the value of x6? It would be 0. It cannot go beyond 0. Why? Because x6 should be non-negative always. So the minimum value of x6 will become 0, meaning that can we make this x6 as non-basic? So non-basic has a no role in the optimization. So in this case, what you will see that currently we have just one artificial variable, which is x6. But suppose if you are solving a problem, and if there are say 3 artificial variable, assume x6, x7 and x8. So our phase 1 says that we have to minimize Rx is equals to x6 plus x7 plus x8. So we want to minimize the summation of all artificial variable. Now the rules which we have gone through till now for a maximization problem. So we are converting this minimization problem into maximization problem using duality principle, that maximization of Rx is equals to minus x6. Now since these are there, so we can use a simplex table now. So here I am writing that from x1 to x5, all of them are slack variable and x6 is an artificial variable. So in the current situation, we have 6 number of variables and 3 equations. So we are going to have 3 basic and 3 non-basic variables for the given problem. Now let us take x3, x4, x6 as a basic solution. So I told you one thumb rule earlier. Let us look at the equation 1, constraint equation 1. Since x3 is slack, take it as a basic variable in the starting. Similarly, equation 2, x4 is the slack variable. We should take it as a starting basic variable. Now look at the x3. x3 has 2 variables. One is x5, which is slack variable. One is x6, which is artificial. So as and when you have any artificial variable in an equation, that should be taken basic at the starting. Why? Because we will be starting taking x6 as a basic, and iteration by iteration, we will make x6 as non-basic. We'll see how. So with this reason, we are taking x3, x4, x6 as a basic variables. Now we have written the simplex table. Now you can make it out. The first row, all of them are 0 and the coefficient corresponding to x6 is -1 because we are minimizing Rx, or you can say maximizing Rx, which is -x6. So please note that we are not solving the original objective function. We are solving the phase 1. So this is what you can say phase 1. The cost coefficient and everything. Now look at the CB coefficient, CB column. Cost coefficient of x3 is 0, cost coefficient of x4 is 0, but cost coefficient of x6 is -1. And rest of the coefficient, we know we have to follow the similar procedure. So the first step is we have to find the delta FQ value for all non-basic variable. So non-basic variables are x1, x2, and x5. So we can see that the most positive are corresponding to x1 and x2. In this case, we can choose any one of them. So we have chosen x2 at random. Now look at the Rx value, how we get it. So CB coefficient and R right hand side coefficient, 0 multiplied by 6 plus 0 multiplied by 10 plus -1 multiplied by 2. So it is -2. Now, since we have identified x2 is going to enter into my table, then what is the leaving variable? So coefficient under x2, which are 0, 2, and 1 will be used to find the ratio. So 6 divided by 0, infinite, will not take it. And 10 divided by 2, 5, 2 divided by 1, 2. So x6 should leave the table. We perform the Gauss-Jordan operation here. In this Gauss-Jordan operation, you can see the x3, x4 are written and x2 has entered into the table. And the corresponding cost coefficient for phase 1, which are 0, 0, 0, are written in the CB column. And rest of the coefficient, you remember, we found it using Gauss-Jordan row operation. Now let us find the delta FQ value for all non-basic variables. So we get 0, 0, and -1. Since no one is positive here, so we can say that we should stop it. And you can also find the value of Rx is 0. So that is the minimum value possible for the phase 1. So we should stop here. So since there is no entering variable, we should stop it. And this is the solution. Now look at the graph. Now the graph says that the origin is infeasible. So what we did here is we introduced the artificial variable so that we can start from the origin. Now I'm going back just to show you. This is our first simplex table. In this case, x3, x4, and x6 are basic. However, x1, x2, and x5 are non-basic. This means x1 and x2 are 0. So that's why we started from the 0, which is infeasible. Since artificial variable was there, so that overall was so for the simplex table, it was a starting basic feasible solution for phase 1 only. After iteration 1, we move in the direction of x2, we get a green point. And this green point, as soon as we get it, as you can make it out from this shaded region, it is already a basic feasible solution. So that's why our phase 1 is terminated at this point. Come to the phase 2. Phase 2 says that now we have to consider our original objective function, which is 2x1 plus 3x2. We can now remove the column corresponding to x6 because it has no role in the optimization. So step 1. So the same table which we have found it in the last slide, we are writing the same. And what is the difference here? Look at the row number 1. Now the coefficient corresponding to x1 is now 2, x2 will become 3, and for all slack variable it is 0. The second change you can find in the CB column. x3 and x4 are 0, but now x2 will become 3. Why? Because this is the cost coefficient in the objective function of variable x2. Now, since at this particular stage, we can apply our optimality condition and feasibility condition. The optimality condition in the last row says that X5 should enter into the table. By looking at the coefficient, if we find the minimum non-negative ratio, X4 should leave the table. So X5 is entering non-basic, X4 is leaving basic variable. We perform the Gauss-Jordan row operation. So you can see the column of basic X3, X5, X2. And now look at the CB column. Since X5 is a slack variable, so the cost coefficient is 0. All the coefficient under this table we have calculated using Gauss-Jordan operation. Again, the optimality condition in the last row says that X1 should enter, and the feasibility condition by finding the minimum non-negative ratio says that X3 should leave. Up to that step, what you have found that we started in a phase 1 at the origin. Then we get this green point, which is the end of phase 1, but the starting of phase 2. Then we started here. The solution which we got in the last iteration was the blue color point. Now I'm going back. So let's look at it. The value of X3 is 6, value of X5 is 3, and value of X2 is 5. So I'm looking at the right hand side RHS column. So X2 is 5, X1 is still non-basic, so value is 0. So that is corresponding to our blue point. Now thereafter, we will again find the delta FQ value. Now once we find out the delta FQ value, before that, in this particular step, we found that X1 is going to enter and X3 is going to leave. So we have to perform the Gauss-Jordan operation. So our simplex table will look like this. Now again, since X1 has entered, you can see the CB column, the coefficient is 2. And rest of the coefficient we find using Gauss-Jordan row operations. Now, use the optimality condition in the last row for all non-basic variable. You will realize that there is nothing which is positive. This means we should stop it. Now, what is the solution? Look at the basic column corresponding to basic, column corresponding to RHS. So the value of X1 is 6, X5 is 6, X2 is 2. What is the objective function value? Look at the CB column and RHS column. 2 multiplied by 6 plus 0 multiplied by 6 plus 3 multiplied by 2 is 18. So this is going to be our optimum solution. Now here I have written a note. Since we have just solved a problem for greater than equal to type where we need an artificial variable, but when you have an equality constraint in your original problem formulation, in that case also we have to use artificial variable, and then we have to use dual phase method to find an optimum solution. So after this, as you can see, we started from the origin red point, moved to the green point in X2 axis. Then we move to the blue point in X2 axis in iteration number 1. And finally, we get the optimum solution as it is mentioned in the graph.